Lesson 1 and Lesson 2 has provided us with important concepts that will play a major role in assisting us to understand Newton's second law of motion in terms of momentum. To make sense of Newton's second law expressed in terms of momentum, let us consider a motion where we have a trolley that moves from an initial position xi to the final position xf. This diagram here shows that the trolley started moving from this position here and it came to this position. Hence here it's dotted to say it's no longer here. It is now at this final point here. It moved from this point here to this point. The object would have the mass m, and this would mean that when it was at the position xi, it will have the velocity vi because it is the velocity at the start position. Then now the velocity at the final position would be v final, velocity final. Because this is a general situation, it could have many interpretations. One may say that the object started with a small velocity and increased its velocity to a bigger velocity here, meaning the object is actually moving fast as it goes to that direction. It is also true to say it starts with a big velocity and it ends with a small velocity, to mean that it is actually slowing down as it's going to that direction. Either motion that you observe will be true in this case. Now, the change in position or the change in velocity would occur for a certain amount of time. That means if we were to take a stopwatch, we will start our clock reading here. We will have our t initial here, meaning the initial time, the time at the start. And as the trolley moves along the straight line, the time will count, the clock reading will count until we get to some final time tf. And so this means that to find the total length of time that it takes for the trolley to move from an initial position xi to xf, we're going to define this as delta t is equals to t final minus t initial. Remember, in lesson 2, I said that when we use the symbol delta, it means we're subtracting final and initial, meaning we are subtracting tf from ti from tf, always. So in this case, we are doing that subtraction for the time, so the delta t, to find the time that it takes for the trolley to move between these 2 points. If you pay attention to this situation, you will realize that actually this object is accelerating to this direction. It has an acceleration a because it is changing its velocity from v initial to the v final over a certain period of time, meaning we have here the rate of change of velocity, and that is the definition of acceleration. To say acceleration is the rate of change of velocity. So acceleration is given by a is equals to delta v over delta t. And of course, we will have delta v here because we will say, because our velocity is changing from initial to final, so we will say here the final velocity minus the initial velocity. In other words, I can rewrite this equation as final velocity minus initial velocity over the delta t. I'll keep the delta t the way it is. I can call this equation 1 for the purposes of what I'm trying to do here. Now let's go back to this situation. This motion can be viewed from a different perspective. What do I mean? I mean that another way of looking at this situation, one can say there is a net force acting on the trolley, and that net force causes the trolley to accelerate. And the acceleration of this trolley is directly proportional to the net force and inversely proportional to the mass. The net force causes the object to accelerate. It causes the object to have an acceleration. And the acceleration is directly proportional to the net force. And this acceleration is also inversely proportional to the mass. At this stage, something should ring a bell in your mind. This statement is what we defined in grade 11 as Newton's second law in terms of acceleration. So I'm going to argue that here, using Newton's second law that we learned in grade 11, the net force is given by the mass times the acceleration. Because this type of an equation makes us to see this relationship where the acceleration is directly proportional to the net force and inversely proportional to the mass. That's how we stated Newton's second law in grade 11. I'm going to call this equation 2. Now, at this stage, I'll solve these two equations simultaneously by saying that substitute equation 1 into equation 2. So that now my equation 2 would be that I have the net force is equal to, I'm going to write the M as it is, but the A, I'm going to substitute this with what we define the acceleration to be. Remember here that this is the acceleration. So this means I'm going to write this as V final minus V initial over change in T. Now at this stage, I'm going to multiply the M with the V final and the M with the V initial, because I'm using here the distributive property. The M has to be distributed on the VI and the VF. So this means here I'm going to have M V final minus M V initial all over the change in T. Because really what we have here is 1. So you can just multiply the 1 by the change in T, you'll get the change in T. It should be clear to you that actually what we have here is the final momentum. Subtract the initial momentum, right? So this can be rewritten as P final minus P initial over the change in T. And therefore, this means that the net force, because remember we were calculating the net force here, is indeed equals to the change in P over the change in T. So what have we discovered here? We actually are learning that this side here we have the net force. We are saying the net force is the same as the rate of change of momentum. Remember that always when we divide with time, rate would mean time. So we're taking a fraction of change in P over change in T. This statement that says that the net force acting on an object is the same or is equal to the rate of change of momentum is the original law that Newton discovered. This is actually the original formula that Newton came about when he did this law. And then later on, when this law was named Newton's second law because he was the one who actually discovered this law. Newton's second law of motion. So this is another way of writing Newton's second law. We say that it is Newton's second law in terms of momentum because it is expressed in terms of the change in momentum. What does this law actually say to us in terms of looking at the physical situation or our motion here? What does it tell us? Well, this law tells us that, remember here that we have the initial velocity and this object has a mass here. This would mean that I can actually say here I have initial momentum because I actually have the mass and the velocity. So I can define this to be mv initial. I have the initial momentum. And also here, I can define the final momentum because again, I have the mass and I have the final velocity. So this law basically tells us that when a net force acts on an object, it causes that object to actually change its initial momentum to a final momentum. It causes a change in the momentum over a given time period. That's what this law says. So at this stage, we have a full-fledged understanding of this motion because net force, actually the parameters of it is that it causes the object to accelerate and the acceleration is directly proportional to the net force and inversely proportional to the mass. But it also causes that object to change its velocity from vi to v final, which that can also be translated to momentum to say it changes the object, it causes the object to change its momentum from the initial momentum to the final momentum. Another thing that we have to notice from this law is that we can look at the SI units here to say that if I were to define the SI units using this formula, we will have the net force, then we'll have the momentum, change in momentum and the change in time. Now, if I substitute here the SI units of change in momentum, I will have a kilogram meters per second when we're dividing this by a second for the time. Now, I will have the kilogram meters. You have to notice that here I have the same base, right? And I'm dividing. That means I'll keep the base, my loss of exponents, I'll keep the base s and subtract my exponents. Remember that here we have an invisible one. So if I subtract my exponents, I'll have minus 1, minus 1. And this means that I'll have a kilogram meters per second squared. And we also know that a force, because this really is the SI unit of the net force here, we also know that a force was given the unit Newton after Sir Isaac Newton. So we are saying here that 1 Newton is actually the same as 1 kilogram meters per second squared. So when we see a kilogram meters per second squared, is the same as 1 Newton. This is just a revision of what we learned in Newton's laws in grade 11. I just wanted to show this again to emphasize the point that we get consistent results even if we use a formula that looks different to what we did in grade 11. Remember, in grade 11, we defined this as net force is equals to mass times acceleration. So we still get consistent result even when we use this new formula that we just derived. The last component that I want to talk about that we see from this new formula that we have of Newton's second law is that the net force is directly proportional to the change in momentum. This would mean that if the change in momentum increases, the net force should also increase by the same number. They increase in proportion to each other. If the change in momentum were to decrease, the net force should also increase by the same proportion as well. And also, the net force is inversely proportional to the time. So this means when the time increases, when it takes longer for an object to move, the force would be small. And vice versa, when it takes a short time for an object to change its motion, the time decreases, the net force should actually become larger. We're going to experience a bigger force. The force that's going to be applied will be a bigger force. We will do some questions to learn how to then solve problems using this new law that we defined.